All right, this is the 3.4 video for calculus, rates of change in the social sciences. Very similar to 3.3, which was rates of change in the natural sciences. But just to do something, I suppose, at the beginning, is yet again, I want to talk about how that average rate of change is your slope formula. And I mean, both are technically the slope formula, but I am going to write and make that connection that the average rate of change is a secant line. And it's the idea that we're looking at, two distinct times, whereas the instantaneous rate of change, I'll just put instantaneous down here, the instantaneous is our tangent line. And that's a really important consideration, that the secant line is over two distinct times, whereas the instantaneous rate of change is at a specific time, which has different uses in different contexts. So the first one we're going to look at is cost, which is pretty important, as you can imagine, for businesses or really for anybody. And it goes over that all over again, that the average rate of change we see is just the use of the slope formula. Important that within this formula, x2 cannot be equal to x1, because then we would be dividing by 0. Whereas in our instantaneous rate of change, because of that limit, it is the idea that the delta x is going to 0, and so it is instant as opposed to the average, which is the equation up here. So way back, or not back, but the idea that the derivative gives us the rate of change is pretty important. We'll be using the derivative quite a bit. The terminology that we use is if the cost function is c of x, then the marginal cost function, and I'll write it in here, is c prime of x, and that's just the derivative process. So we'll do a couple of these, and typically students like these kinds of questions. So it says a mill company produces flour. The cost to produce 5 kilograms of bags of flour is estimated by using that function, where x is the number of bags produced. A bit of a distractor here. This 5 kilogram bags doesn't really matter. That's just the size of the bag. It's always a good idea to think about what the variable represents, and in this case, x is the number of bags produced. We don't really care what size the bags are. So A says the marginal cost, and I'll just write that yet again, that marginal cost is c prime of x, and it wants us to do that at a production level of 1,000 bags. So x is 1,000. Now what that means is that A is essentially just asking for c prime evaluated at 1,000. And I hope logically the way that we're going to find that is to find c prime of x and then make a substitution. So c prime of x, we're using a bit of power rule and the sum and difference, taking that derivative term by term. What I get is 0.43 plus 0.000002, and then x to the power of 1. So we'll just leave that as x. Now, the remaining part of part A here is the idea that c prime of 1,000, we're going to substitute 1,000 in for x, and I'll tell you the answer here. In dollars, it is 0.432. Now, I actually don't like putting the dollar symbol there. I shouldn't have done that. It is good to think about these units. And C, the output of the function, is in dollars, and X is the number of bags. So this is the dollars per bag. Now, what's really important is that's the actual marginal cost. That's how much the cost of making a bag is, or the cost of making the bags is going up by. Now, to find the actual cost, and I really like the idea of describing that as delta C. And if we're looking at the 1,000 in first bag, then delta C is equal to the cost at 1,001 bags minus the cost at 1,000 bags. Plugging that into our formula, I'm not too worried again about you being able to show this. It's not a very bad idea. I'll write it in now that I've talked about that. This is going to be 140,000 plus 0.43 times 1,001 plus 0.0000, gotta make sure I have the right zeros here, 1, and then that will be 1,001 squared. Ran out of room here a little bit, but I will be subtracting that function evaluated at 1,000, which is 140, I think I forgot a 0 up there. There should be one more 0 there. So 140,000 plus 0.43 times 1,000 plus 0.12345, and then 1,000 squared. All right, really important that that negative would distribute, and what I end up with is the change in cost is 0.432001, and that would be in dollars as well. And we see that our derivative is very, very close to the actual cost of increasing that production. All right, so we'll do probably one more example here, and then I'll split it. You know what, I'm going to split the video here, and we'll do those last two examples.